So the first step is this WCS refinement step, which is tweak reg, basically. So it's going to refine the JWCS. So here's a link to read the docs, the description of the step, and then here's a link to the optional input arguments, which we'll see in a second. And so what I'm going to do here, I'm just going to use the run method so that things are not quite so repetitive. Again, here are the parameters that you can vary with this step. So what we're going to do here, similar to when we call the pipeline, right, with the run method, we create an instance of this step, just like we created an instance of the pipeline before. Set the parameters in basically the same way. So instead of being, model dot whatever, it's just tweak reg dot. And then you call the run method and you provide the association file. It should go relatively quickly. And so the log that comes out here is very similar. It's essentially a portion of the log that we saw before with the pipeline itself. You'll see, in this case, here are our 3 input cal files. And down here at the bottom of the log. So this is a little bit strange because we're running the step itself instead of the step within the pipeline. So in this case, the output files are being saved into these tweakreg step.fits files. We define that. In this case, what I want to do, I'm going to use the data models to open these files. I'm going to open one of our input files and one of the output files, the corresponding output file. What I'm going to do here, so Alicia went over this a little bit more in depth in the first JWebbinar, but I'm going to go over it here again just because it's useful and important. So what we're going to do using the data models, we're going to go into that ASDF extension and grab the JWCS. And we're going to create functions that will allow us to transform from pixels to RA and back. So here you see, here's the cal data, input data. You use the meta attribute that contains all the metadata. We're looking at the WCS, and then get transform. It's this get transform function, we want to transform from detector coordinates to world coordinates. Then we'll do the same thing for the output data in this step. So we'll define those 2 functions. We'll choose just the pixel that's right in the center of the detector. And then we can call those 2 functions on that pixel. And so here we have the RA and the DEC before and after the step was run for that pixel. So this way you can kind of get an idea of how big of a shift tweakreg for this data. You'll see in this case, there we go. So we'll use our functions. We'll make this a little bit more readable here and translate, and we see that the shift is thousandths of an arc second and hundredths of a pixel. And so in this case, that makes sense because our 3 cal files were just simulated data, and the data simulator tool that I use to create them doesn't put in jitter or uncertainties in WCS. So this tiny shift is what you would expect. Just to show you, so here we're just going to look in the metadata. We're going to look at the WCS, and so you can see there's a whole lot of stuff going on here. But essentially, what you've got is a series of functions. So you've got a shift, some shift functions. You've got some 2D polynomials, some more shift functions, and these are all serialized in order to create these functions that will go from detector coordinates to RA depth. After this, we come to the sky match step. So like Carl mentioned, this looks at the overlap regions between the input images and figures out the offsets in the sky. There are a few optional items we'll look at. Just like before, we'll use .spec. Look at the available parameters, and there are a bunch in here. So I'll point out there are a number of different ways that you can have it calculate these sky values. And so I encourage you to look at the documentation to look at the differences between them. So some are good, if you have a lot of overlap and a lot of empty sky between your objects. Some of them are better if you have some large extended object filling a lot of the detector. So in this case, what we'll do, like before, we create an instance of the sky match step. We're going to set the method to be this global plus match, although that is the default here, you can see. Save the results. And so in this case, since we're running step by step, I'm providing it this tweak, which was the output of the tweak reg step here up above. Here. The tweak, in this case, is actually a container that contains a list of data models. So it contains the 3 data models for our 3 input images. So I'm going to provide this as the input for the next step. It would be totally fine to provide an association file for this if you wanted. The downside is that since we created these new tweakreg.step.fits files, you'd have to create a new association file that lists these tweakreg.step files. So rather than go through all of those hoops, I'm just going to provide the data model container as the input. This will go off and compute the sky values. And so in this case, the default behavior is that it'll find the sky values needed to equalize the sky. And it'll save those data values in the headers, but it's not going to actually change the science data at all. Those sky levels will be read in and used later. And so here, all I'm doing is getting the header from one of the output sky files, and I'm looking at these new keywords that were just added, so BKG level and BKG sub. So you see there's some background level computed. This is Megajansky's per steradian, and background subtracted is false. And so this keyword will tell you if the background is subtracted or not. There is a way to turn on background subtraction during this step if you wanted to. And so again, let's use data models to open one of these output files. And just to show you, here we're just looking at the data output from this step versus the input versus the cal data, the science data in this case. And you can see that the differences between them are all zeros. So the science data have not been changed at all. So next, we move on to outlier detection. So this is kind of like a more traditional cosmic ray finding algorithm that will look at the overlaps between the 3 images and look through the stack, and if one has a source and the other 2 don't, then it will flag that source. And so what happens in that case is it updates the flag in the DQ array. Again, it doesn't change the science data at all. And then later, when the mosaic is created, it will look at those DQ flags, and it will just ignore pixels where the flag has been set. Here we've got a long list of possible parameters to play with. They look fairly drizzle-like. So in this case, we're not going to play with any of these. We're just going to create an instance of the step, say that we want to save the results, and then use the .run method. And again, I'm going to supply the data model container from the sky step before. Here, the output files in this case, right? So this step takes a little bit longer because it actually does call the resample step, because it needs to remove the distortion from the input images in order to correctly look at the overlapping regions. This one takes a little bit longer. Like before, the output file names in this case, because we're calling the step itself, are a little bit strange, but they end with outlier detection step.fits. Okay, so we're finished. We're going to use data models to open this one. And so what I'm going to do in this case is just look in the DQ array to look for the new flags that have been added. So I'm using NumPy's where function. I'm looking in the DQ extension of our data model. This is in fact the data model of the original input data, the cal file. And I'm just looking at where those DQ values are different from the DQ values in the outlier detection output. Up here, we found 28,500 pixels that have changed flags, have modified flag values. Let's just choose one of those 28,000. We'll get the XY value on the detector and just print out the flag values before and after. So you can see we've got this large number. You can see that they're slightly different before and after. In order to make this make a little bit more sense, we'll use the convenience function we defined above, and that will break this number down into the various component flags and what those component flags mean. So you can see in the input cal data, this pixel was already pretty bad. It was flagged as bad in many different ways before we even got to outlier detection. And so after outlier detection, we look at the same thing and we can see this outlier flag is new, and that corresponds to 16. And you can see that these two numbers here are different by 16. So I should point out, if this pixel had been good before outlier detection and had no flags, then after the outlier detection was run, you would get this outlier flag with a 16, but you would also get the do not use flag, which is a 1. So the final value would be 17. And then just to show that, again, the science data has not been changed. So here we look at just the science data value for this particular pixel. It's in fact 0. So this is actually a really bad pixel. Once that is done, we move on to the resample step, and we can actually make our mosaic. So there are, again, kind of astrodrizzle-looking parameters that can be set from kernel. Or other steps. We'll create an instance of the step. We'll save the results, and we'll use .run, providing the data model container from the previous step. So this is very similar to what was done in the outlier detection step. In that here again we're drizzling from the original 2K by 2K to 2166 by 2169 pixels. Takes just a minute. And so again, in this case, because we're running the step itself rather than the step within the pipeline, the output file is going to be called this, resample step.fits. So that finishes the image. Is there a better way to recover saturated pixels from the ramp data? So in JWebDetector1, like Carl was talking about, anything that's saturated partway up the ramp, the groups that have been saturated are thrown out, and we fit a slope to just the remaining groups that are good. Any pixels that happen to be saturated in every single group up the ramp those are left with a slope of 0 at this point, and there's really nothing you can do at that point to recover those. Resample is finished. We see the same. This is essentially the same mosaic that we saw up above when we ran the full pipeline. And let's see. Just to show if this has been resampled onto a distortionless grid here. Right? The grid size is different than the input grid size. The last step then is the source catalog step. The .spec attribute again. You see we've got a few parameters we can play with here. So let's run this step and set parameters kind of similarly to what we did with the pipeline call above. So we know the PSF forward half max, so we can set that. We want to save the results. We bump up the signal to noise threshold, right? I think yes, the default is 3 sigma, so we'll bump it up to 10. And then we'll do .run, and we'll provide, in this case, now we're back to having only a single file, single fits file, so you can give it a sample file. And so again, just like with the pipeline up above, this just shows if you wanted to use the call method to run this step. So here, we downloaded this parameter reference file at the top of the notebook. So if you execute the cell, you can have a look. So again, in this case, the important thing here, we've got the name is source catalog, and then the parameters, and these are the parameters being set in this case. If you wanted to use the call method, it would be basically the same thing, source catalog set.call, provide the resample file, and then your parameter reference file here. And then you can also save results explicitly on the command line. Then for strun, it's very similar to before. strun, and then the name of the parameter reference file, the name of the file, and the name of the file you're working on. And then if you don't want to provide the parameter reference file, or you want to set things manually on the command line, you can set them with the --. So, okay, so that's done running. Open this up. Here's the same table that we looked at up above when we were in the full pipeline. Again, you can overlay the catalog on top of the mosaic.